Good afternoon, everyone. I hope everyone is good. Um, Let me just check how many we are. We're gonna start in a few minutes. Let's just give some um, 1 or 2 minutes for the rest to join in. Um, so for today, we're gonna go with our topic for our webinar, and I can see a lot of people joining our webinar today. So everybody just want to check. Hopefully everyone can see my screen and no issue with the connection. So if you have anything, you can put in the chat. You can let me know, or in the question window in your screen. So you can send me feedback in regard to the presentation, or you can also ask questions about it. Just give till some people joining our webinar for today. Okay. All right. I think we can start, and we have everyone. So welcome everyone to this webinar that we'll be sharing with you about some of our insights and our innovations on about electrical architectures that have been adapted to data center today. So thank you again for this privilege of speaking with you and able to share with you some information from us from Socomec. Let me just get my screen settled. So for today, I'm Rayson Luzano. I'm the APAC PCO business developer. We're gonna go through our topic, which is the data center architectures, efficient and optimized data center architectures. Just to start with a quick overview. Of course, some of you have known Socomec. Just a quick overview of what Socomec, who is Socomec is. We are an independent electrical equipment engineering manufacturing company. We specialize in low voltage performance devices. So I'm happy to share that we're celebrating our 100 years of foundation in energy market. So we have been developing different technologies in power switching, power conversion, and power monitoring design. So with the technologies, we also have products. We have products and equipment onto this type of business, and also we couple them and we enrich our propositions with the added services. So as you all know, Socomec is present in all major market segments, be it data center, healthcare, or energy, or anything else. You will see Socomec common. I think even in any part of electrical system, you will see a Socomec logo there. So like many other companies, you can see Socomec is one of its core strategies is sustainability. We are so proud to say that we are part of the 1% out of 45,000 global companies that's been rated by EcoVadis. Right? It is important for us because it's our future, it's the future of our children, that we do our part and take actions to the commitment and answering the climate change. Some of the examples that we have done in our sector is getting our manufacturing certified ISO 14001, and of course the continuous installation of installing renewable energies to our all facilities in our friends and Italian facilities as indicated. So without further ado, let's start with our session. Before we start, I just want to quickly have a quick poll, right? So since we're gonna talk about designing electrical architecture, so I have a poll here. Let me just run it to you. So we're gonna have, I want you to select, so get your mouse ready. So select, I would say, let me just see, oops, where's that? Oh, not this one. Okay, So I want you to select three, right? Your top three criteria, right, in designing an electrical infrastructure. What will be the first three? I would say whether it's going to be efficiency, sustainability, availability, or resiliency, or maintainability. So let's see. Get your votes done, right? So we see what are the top three that we take into consideration when we design electrical. Of course, cost is one. I didn't put there that's mandatory. We know cost is always been in the design portfolio. However, let's focus on these five major ones. Okay, so we have four. Half of you have voted. Uh, Keep on voting. So far, let's see what's the trend today. What's happening as designer in this field? What are we? Uh, what are our main criteria? So, okay, I think, let me just close. It's already 1 minute. So let me just close. Now, all right, let me see. I can share the poll results. I think you should be able to see them on your screen. So 75% majority efficiency and maintainability, right, are must, followed by availability, sustainability, and resiliency. Those are all at 50%. So in overall, the top three will be efficiency, availability, and maintainability. Interesting. Okay, so those and you are right. Majority of us we have seen those as part of our design. So it's very important for us to do so. So as we can see, we're gonna talk about a lot of architecture today, and of course we're gonna in particular we're gonna look on the UPS, right? UPS as our reference for this topic, because we all know UPS has been in the backbone of all data centers, and as we all know, as the power demand have increases to these data centers, we have seen the size of the UPS also continue to rise. Back in the days when I was in different UPS company, we thought that the UPS will become smaller and distributed, but it happens. It was the reverse, right? We have seen larger UPS installed. So, and also UPS architectures have changed, and we have adapted new requirement. Not only as I think as we can see in the poll, not only efficiency and availability, but in today's world, sustainability is also one key thing. So I've been seeing in a lot of tenders specifying what type of sustainability actions these companies are doing, more of an environmental solutions as well as resiliency, because we need the moment we try to execute and optimize our architecture, resiliency will be one key thing as well. So, and of course, maintaining it are some of the criteria being highlighted, just like in our poll. So today we're gonna go with the different architectures and how it has shaped us as a manufacturer, how we design UPS and what technologies that we bring from there. So how we can optimize them and how we can make them more available and efficient. So if you look our webinar, we'll cover four basic quick parts. Of course, we're going to talk about some of the DC standards, data center standards that we've seen, especially the 2N, to have that reliability. We're going to talk some of the redundancy architectures, distributed redundancy, the block redundancy, and at the end, we're going to look on something what Socomec is doing. So as you can see here, we got Delphis Excel and some of the innovations that we can see in the future that will be looking in the market. Just share you some crystal ball on what's happening in the UPS market. Anyway, to start with, we're going to look on the first topic, our data center standards. So and covering the 2N system, which provide us the redundancy that we have, right? So I know everyone is familiar with the chair standards or chair classification. So this has been done in more than 10 years. We have seen these chair classifications that provides the level of redundancy that to the availability of the energy powering the critical loads in our data center. So the world have seen a lot of this, right? So we can see different flavor of it. So there are some publications from different organizations, like the Uptime Institute. You can see that they have this same chair, and of course, and also provide these as a certification for data centers to comply to certain availability models. So the certification may not be compulsory, but many data centers follow these as a guideline. So as we all know, in most of our design, we're going to look mostly on the tier 3 and tier 4 classifications, because they are the one that provides redundancy as well as concurrent maintainability in terms of architecture. So if you look on the tier levels, you're familiar with it. The higher the tier level, the higher the level of availability. As you can see here, tier 4 is 99.996 availability. So on the other hand, we have other hardware in the system, not only looking on the UPS, but also there are some cooling equipment, IT equipment that flows onto this tier classification as well. But for today, we're gonna look specifically on the electrical side. As you can see here, also one of the company organization, mostly in America, the TIA, that's American standard, found in America, right, in the US. So it's most of the tiers certificate classifications are based. So you can see these are all been adapted in Europe with the EN 50600. So they've been it's basically all based in the TIA chair standard. Yeah. Even though we derive from different, we call it class in the European market, but it's actually the same, right? So there's also one organization, so there's a lot of them, the Building Industry Consulting Service International, better known as BICSI, is also have the same task. So they create performance criteria in which different data center designs can be judged or certified, but also not only considering the power, but the whole entire data center, right? Whether it's going to be an IT, availability, power, cooling, and network as well. As I mentioned, for today, we're going to focus on two major classifications, which are class 4 and class 3, or tier 3 and tier 4. So we focus on these two typical architectures because, as I mentioned, they achieve the redundancy that is required, and also the maintainability, the concurrent maintainability option that we can perform with this architecture. So you can see on the schematic, there's some comparison on your screen right now between class 3. I'm going to call them class 3 and class 4 because we are in the IEC region, or we can call it tier 3 and tier 4 if you're looking about tier standard. Anyway, they are the same. The concept will remain quite the same, exactly. So as you can see, what's the difference between class 3 and class 4 is, of course, you have two powertrain channels, or we call them channels, channel A and channel B. The main difference between class 3 and class 4 is a UPS on one channel compared to two UPS systems on both class. So basically, in a class 4, you will have both A and B channels are live, basically. So you can have two active channels running on a class 4, comparing to a class 3 where you have a redundant channel that will be brought for our tier 3 or class 3 application. Looking on or more detailed in a schematic as a representation, as you can see on the screen, you get the whole entire distribution architecture of a class 4 or a tier 4, or we call it 2N in our language in redundancy, with the different paths. So you can see A and path in A in blue and yellow in B, right? So each channel, you can see it has its own generator sets and transformer and separate source, because this is necessary to maintain two two systems, right? So you can have the redundancy. So your HB and feeders are all dual supply. So if you're gonna look further, as you can see here in this schematic, you can have a sample of a two-end solution. So you can see there are two sides with its two channels, provide full power for the total IT load. So you can see on the screen, even you have dual core server that is supplied on the left, and also there's another supply on the right. Right? So this is called what we call 2N. I think everyone is familiar with it, right? So as you can see here, you can have your IP loads, and in some cases as well with the same UPS, we supply also some of the non-brake mechanical loads like controllers and the FCUs or the chiller pump motors. But also in most of the design, we separate those. So it's also what we have seen as a best practice. We've seen on data center implementation that the mechanical loads, the non-brake, we call them non-brake mechanical loads, are being supplied by a separate UPS. So we can see this is on the range of 200 to 250 kilowatt, typically on what we see in data center design. So we have separate IT loads, separate UPS system for the IT loads as well. So some of the mechanical loads doesn't need because they will not create any disturbance, because as you know, temperature doesn't rise as an instant. So the water temperature, so we can on a chilled water system. So they can allow a few seconds of power losses when the genset kick in. So in order to restart them, so it will not have any much impact compared to the critical cooling devices like chiller pumps, the controls, or the FCUs that needs to be always on in terms of UPS protection. So here's an example of a single line, a diagram of a 2N solution with separate, with distributed architecture. Right? You can see a separate UPS for our IT load, and of course we have a UPS for our mechanical load, as you can see here. So if you go to the data hall, you have your two systems. I think just a review. You have your A source and B source, which will be powering the system. So as you can see here, as an example, you have a 3.6 megawatt power pack. Both of them are running on a half load or 50%. So in any one that one of those sources fail, you have the other one will be able to handle the rest. So it's typical 2N, right? So it's been there in the market, and it's been adopted. Right? But what's the best one, right? What's the best architecture that we can see, right? The answer is it depends, right? Depending on the data centers. And you all know we have different types of data center. Just a quick recap. So we have the type of edge data centers. These are mostly on like in telecoms and corporates, right? And of course, we have the large data centers called co-locations and hyperscale. So depending on the purpose, on the applications of data centers, that will depend the type of redundancy that they need, because how they grow, how they implement their the servers, it will depend on the type of UPS and architecture that you will see. So you can see this. You have the edge, the telcos, the co-locations, and the hyperscale or the cloud providers. So if we look more on the edge and telcos, they are more in a sense of conservative approach. So meaning, if you look on how they implement their data centers, they're focused mostly on energy availability to be achieved. Right? So they're going on scaling, right? So because you don't know when their customers or their application will be adopted. Good example is 5G, right? Not all places will have 5G at an instant. So they will roll it out phase by phases. So how they design their data centers will be more on a scaling. So as you can see here, we go move by move and add zones. They call it zones in adding to their system. An example, a good UPS in this case will be a modular UPS where it can be scaled because they can install at a low load level, right? Low capacity in the beginning. Good here is our modules Excel. So you can start with 200 kilowatt, and of course increase that load, that capacity as you go on to your higher load. So they are more in those kind of approach. So their evolution or their load increase is in the equipment that they have. They run through phases. On the other type, of course, as we can see on the other spectrum, sorry, the other spectrum is the is on the collocation and hyperscale. So here, it will be mostly on a cost optimization approach, right? So, and the scalability is not on the electrical infrastructure, but on a data hall level. So as you can see, in these applications, some of you have implemented or work into an hyperscaler colocation data centers. As you can see, they have different data halls, right? So first data hall, their phase they will introduce. And then they have a computer room and adding a pre-standard design data hall and add it on the next. So as they scale up, right, as the requirement, as customers or tenants starts to be hosted, so they evolve or they add capacities into their data center. And one major thing here, one key criteria for this type of data centers is space, right? So because for them, space is money. So you can see on how they optimize their electrical system. We even seen customers looking on putting on containerized solutions, right? Putting out their electrical system outside the floor, data center floor, so that they can have those space that they need, right? So as you can see here, they scale by data center hall, right? So if you look, so those are the typical data centers on how they scale up. So how those with two-end solutions, right? They're looking in ways in optimizing it. So that's come to our distributed redundant system, right? Some of you are familiar, we are all know. Let's look, what are the available redundant system we see in the market today, right? So here we can see the very famous one that we have discussed earlier. The concept that we have seen is called the 2N. So you have two source, right? If one source fail, the other one will be able to take up all the loads of the whole electrical system. So this is the 2N. And on the next one, we have a 3 and 2, right? Or three source with allowing you one system or one source can fail, and so on and so forth. So we have the 4N and we have the 5N. Probably it's time for another poll. Let me just see if I can add here. Right, I have here. Maybe give you a poll again. Let me know, based on your experience, which one is the most common distributed redundant system that we have seen in the market, system or architecture. Is it 2N, 3-2N, 4 and 3, and of course 5 and 4. So I have set up the poll. Let me know, what do you mostly see in the market? You can see there, yes. Okay, I can see everyone voting. So we see, oh, majority is 2N. Okay, vote more. We can have a feel. Right, I've seen 4N. Wow, okay, good. Yeah, I've seen 4N. Nice. Okay. All right. Yeah, I've seen 4N as well. Okay. We got more 30 seconds. 30 seconds to vote. I'll give you 1 minute for this. Okay. Keep on voting for those who are inside. Okay, good. So we have 10 seconds to go. All right, and I'm closing the poll right now. Okay, let me share you the results. Okay, here. You should have seen here, majority, 70% we're still doing the 2N. And slowly we're adopting 3N, we have seen. Now, quite a few of us have seen 4N. For me, in my experience, I've seen 4N. My biggest challenge there is synchronizing all the UPS, all the system sources, because when you do transfers, you need to synchronize. And with synchronization, you have an issue with the reference because you have 4 reference. So we need to make sure that they are referencing into one. But again, you are right. Majority are still using 2N because it's the most easy and easy to implement. And later we're gonna see one major thing: the challenges when you start to make use of more optimized solution. The main thing as we grow the number of sources is where the optimization will go, right? So you can see in principle, right? So you will have smaller UPS, you will have smaller capacities, meaning smaller cables, and also a smaller transformer and easy to scale. So those are however, there will be some drawbacks that we need to pay attention, right? What are the drawbacks that we can see when implementing this type of redundant systems, right? Just a recap, as you can see here, we have the 2N. If we have a 1.2 megawatt of load, 2N means you need to double it. So you have 2 units of 1.2 megawatts. So you have a total power installation of 2.4. When you have this, it's not only your UPS, your battery should be also 2.4 megawatt, right? So you have a utilization factor. That's why some architectures have went into 3 and 2, right? So they want to optimize it by using smaller UPSs, and they have more and capitalizing optimizing the solution. In this example, with the same load, we can use 3 units of 600 kilowatt, and we will have a utilization factor of 1.5, as we can see here. And as we go on the design, right, the better we utilize for 3N. We can have 4 sources, and in normal mode we can share the supply, the load, and when we turn off, or when one system is up, we call it a degraded mode, right? So 3 sources can be able to supply the load without overloading, right? As you can see from here, and so on and so forth. So for 5N, as you can see, it's the same. So the more system, the more sources, the more optimized. Of course, the more system is also the reliability, the distribution. A lot of drawbacks also must take into consideration, right? So in summary, you have realized here, the more you multiply the downstream sources, the more you reduce the power, as we can see on the previous calculations, right? So to ensure the redundancy, we need we can also reduce the investment cost, right? The maintaining the system. Of course, smaller boards, smaller bus bars, and all those things play in the picture. And look, everything is well as you go complicated, right? Here is a representation on a quick example on how the system works. Everything is in ideal position. We have distributed. You have 3 units of 600 kilowatt, and maintaining a load of 400 kilowatt. Because if any of those system goes on downgraded mode, you will notice that that load will be transferred to all the system, right? But if it is above here, there will be a possibility of an overload on one of the system, which can cause a big problem in your installation, right? And to become more complicated when we go with a 4N solution, right? 4 and 3, where you have multiple power train, right? So you can see here in the diagram, this is an example of a co-location data center. There are 4 power supplies in channels distributed in the data center hall or the IT room. So you can see they're powering multiple pads, multiple server pads in the solution. If we look closely, right, how we can maintain, right, the reliability of design, right? And one key thing plays into picture is balancing, right? It is the main challenge when we have the more systems that we have powering multiple channels. It limits us, right, on how we balance, making sure the right load will go to the right phase, to the right UPS, right, that will carry it. So again, that's the big challenge we have, how we can balance on distributed redundant systems. If you look here on a two-end solution, everything is great, right? You have simple. If your UPS is running on 50% load, you're all good, no problem. Because if anything goes wrong, the other system will be able to take care of it. You're sure, right? You just need to make sure here. I think it's a best practice. Whatever A source or the B source on source A, the line should be always on the same line, so that you will ensure that the same current for each line will transfer to the same line as well. So that's the only one you need to make sure that simple management. Okay, but it goes above 50%, and that's where your problem, of course, because the other UPS will not be able to handle the full load. That's the problem with 2N, right? So you maintain at 50%. And this goes even more complicated as we go on with the 3N. So as you can see here, the load changes. We cannot dictate where the load will go. When they reach certain capacities, and when you go to downgrade mode, there is a possibility of that load moving to the incorrect system, right? So it may cause, depending on those systems, right? It can cause an overload, or the moment you add more load, because these are all happens in dynamically in a data center, right? So as you can see there, when you go on downgrade mode, or one of the leg is disconnected or on maintenance or whatever, you have the possibility of overloading a system, and this can create a chain reaction to the whole design. So balancing, right? Balancing is the key on how you can maintain balance in your electrical system. This can be achieved in different ways, right? If you're familiar, of course, with monitoring system, you can use monitoring system. You can see the market, right? You can set thresholds for your IT engineers, or your customers, or the operators, to make sure that they plug it to the right device and send you alarms in case that you have reached the highest or a threshold that you have set. So a DSIM or an energy management system will play a big role on the balancing, right? Another system that we want to talk about is the block redundant system. We all know about this one. We have heard about it, but before we go to block redundancy, we're going to talk about our STS, because it's integral, it's part of any system. So how it's function in this block redundancy system. So as you can see here, it's standard configuration. Everybody happy. You have source A and source B, right? Everything is good. It looks good and clean, right? You can see there. However, in real life, when everything goes in, when the system goes on operation, we have all those issues, right? Internally also, we know servers have dual power supply, and there is a possibility of a PDU failure that all the servers are connected. So with this, you will have also a downgrade of reliability or have availability on one source. So as you can see here, that can cause a downgrade mode of that server, because it's only getting from one source as well, right? There's also a possibility that the PDU is connected, or the server is connected to the wrong PDU. So even though it has two outlets, two inputs, but they are connected on the same source. So this also provides an issue or a point of failure that the server will be also down. So, and these are all things happens typically in the data centers. If you don't have proper workflows or proper control in installing or in the data center management, right? So as you can see it here, these are the common things, and that's where an STS could bring benefits into the architecture, because they can put the reliability upstream on the higher level, right on the PDU level, where you can, and the server doesn't care, right? They will still maintain the redundancy that they needed. So that's where STS would play a big role. In addition, of course, when we talk about STS, you always know they are a point of failure because they're on the main system. And one thing also we need to consider is the short circuit, because short circuit can go anywhere, right? So it can be from different distribution, and how that is managed, it should be managed by our STS. Again, different STS in the market, but in Socomec, as we can say, this is how the STS will work. So if there's any fault condition on the downstream, you will see the STS should lock itself, right? So that it will not propagate the fault to the other source. So that will ensure the reliability and make that fault clear by the either through the inverter of the UPS or to the bypass channel, right? So that's how a STS will work in the system. Okay, so you need to lock. So going back to our discussion on how a block redundant system, or what we call a catcher. So this is a simple thing. As you can see here, we have now a 1.2 megawatt UPS, and there you go. We have our STSs that provide the redundancy. So you can do this. You can have multiple data center hall, especially on colo and hyperscale, and you can have a single redundant block, or what we call a catcher. So this could be implemented. So it's like an A and B source typically. So you have your source B as your UPS catcher, but also you have your source A as your main UPS. However, of course, the catcher won't be optimized if it is only a catcher of one system. So the catcher can be a catcher of multiple systems. So this is where all your savings will go, right? So you will have less UPSs, meaning less UPS, less batteries as well. So with this architecture, you can ensure that its supply, or including the catcher, right, are all equipped with static switches, and they can supply the required power in case one system will fail, right? Even though you have imbalance, right? Imbalance on the load, you can see here we have different 750 kilowatt on the blue pot, etc. Right? So you can make sure if anything goes wrong, your catcher, that 800 kilowatt from one of the system, will be able to provide by your catcher system, and that can be transferred in as fast as in milliseconds. So we have done this testing on one of major customer, and they are happy with the result, right? So we have a capture solution in the factory and with an STS, and we capture it, we test it, and it's the if we zoom closely on how the system will interact, there's almost milliseconds, right? So the load will not be able to see any disturbance in the system. So with that, of course, if it's viewed, right, as an optimized system where you can achieve better redundancy, and of course lower footprint in terms of your installation costs for your UPS and batteries. But of course, as manufacturers, as these architectures changes, right, we need to define a system that is right-sized to it. So on our next slide, we're going to show you some of the innovations that we have done in Socomec. So in order to complement these architectures when we want to optimize them and make them more effective. So as we can see here, we have just want to introduce to you our Delphis XL. It is designed for a flexible, right, as we go on, and a resilient and maintainable system. When it goes to resiliency, this kind of technology have been into the market, what we call the brick technology or the modular. However, of course, not all brick are made the same, right? So they are brick that are not resilient. So one of the integral things that we have put into the system is how we can make it more reliable, making sure that the fault does not propagate to the next module. So we have fault containment and isolation to make sure it disconnects from the rest of the system. So the system will be able to continue to operate even though there's one brick that have failed. And of course, you have a bigger brick here. We have around 240 kilowatt of brick. And you're gonna ask me, Raisin, yeah, that's so big. How can I service it, right? Of course, it comes with an easy pull. You can put it out, and when you put it out of the system, I'm a service engineer by trade in my life, so I know how difficult to service a UPS. So getting the whole axis in front and sides of the system allows me to repair and troubleshoot the system fast and easy. Of course, if you have all access, you can easily and get the repair faster to the customer. And in addition to the intrinsic redundancy, the fault propagation, so the fault will be contained on the module. So this would mean less spare parts for me to replace. Of course, less spare parts, faster repair, and less cost to the customer. In this next year, in Asia Pacific, we'll be introducing the maintenance box or maintenance panel that you have here. This will allow, it can be installed in a building, right? If you have multiple UPS, and you can test the UPS brick into this box, right? And you can perform 100%. You can do your internal testing of the hoods after repair, and you are confident after any repair you got the system running 100%. Or it can be a spare as well, right? So if you have a 40 module or 40 brick, you just can get the spare one and insert it to and replace the 40 module inside your UPS. So one thing also, the moment you have all the system, again, the flexibility in cable wiring. You know, I've seen the UPS evolve in the years I've been in the industry. Everyone make it smaller and smaller and smaller and make it more efficient. But how small we can do, right? It's all the cabling and bus bar. So again, what we need to ensure is the capability and flexibility to connect different types of electrical connection, whether it's going to be a bus bar or cables on the top cabling entry or a bottom cabling entry. And of course, integration with other connections like bus bar plunges. We have seen how the UPS evolved in the market, right? So how the technology in IGBT is becoming more efficient. So now in IGBT, standard IGBT 3 level, we can achieve 97%. It's a market standard that we have right now. Of course, if you want further, you can go what we call a smart conversion. So it's basically running the UPS through the static bypass while maintaining the power factor and your harmonics on a low level. So we call it smart conversion. So it's basically interacting with the line that provides a good power quality feedback to your upstream, and of course you can make sure that it is safe. Right? There will be no harmonics, no changes in the power factor. And one thing that we've seen in the market as well is the grid support functionality. This is known. Is becoming we are becoming more aware of this, basically with the introduction of renewables in the grid. So we have different aspects that disturb our grid, right? So and one of the good candidate that we have in the market to provide frequency reserves and frequency regulation are UPS, because they're a lot connected to the grid, and it's a ways that we don't utilize them. So some of the countries are already implementing this, especially in Europe. I mean, Australia, we have, right? We have the authority, the grid authority that allows data center to load shed. They can be triggered to remove some of the load during peak demands, so that they can turn on their secondary reserves. And all other applications, as you can see here, about peak shavings and all those things, can be performed using the grid interactive codes. Of course, if we go closer, lastly, of course, is when you look the system, you just don't look on the UPS. You need to look, because the UPS is not just a box that you put in the electrical system. It will interact to your upstream as well as your downstream. We have discussed about STS earlier, how the STS will work with the UPS in providing the fault and locking the port to make sure that the downstream breaker will be isolated, right? On top, we all know that the UPS interact with the genset. I think everybody knows those in the UPS market. We have this function called ramp up, right? So every time we transfer from genset to utility, we are able to ramp up the current going to the genset. So the big problem is when the genset is running, the load changes can still happen. And in this time, the UPS still monitor the output of the genset, making sure it will stay on certain condition or ranges. So if it sees the voltage of the genset or the frequency changes, it will allow a power sharing from the battery to maintain without getting the genset unstable output, and it will lead to a full battery operation. So those are the major changes, major technologies that we have in the system. So from looking on our architecture, starting from a 2N solution, right, where we have everything is doubled in our implementation, our equipment, our cabling, our batteries are all doubled, and we lead to distributed redundance, where we can have optimized solutions by using different architectures, right? So we can optimize the capacity of the battery from 3N2, 4N3. However, all these type of architectures create drawbacks, right, in our installation and maintenance. So we need to put additional design criteria to ensure they will operate the way we want them to operate. So of course, by load balancing was one of the key challenge in implementing this type of architecture. And of course, moving on to block redundancy, where you will have the introduction of STS, right? So in this, where you with the combination of a hybrid, I would call it a capture system, with you can optimize the footprint, the number of UPS you have installed, the cabling, in addition to maintaining that redundancy that you require. And of course, by complementing it with the right UPS that you can see in the market that is resilient and maintainable, and that will give you a better stand in your design. And I'm happy to share that one of our biggest data center in the world basically have been adopting this kind of technology or architecture into their co-location data centers. So in the next question is what's next, right? So what's next? We can see in the UPS, right? I have been working in this industry for quite a while. What I can say, AI is coming in. Actually, there is already a working technology that is out there utilizing AI. It's similar on what we use in cooling. You know, in cooling, where we can perform, where we can baseline the cooling requirement us by the time that is the load level or the load profile. The same thing with UPS. I think that there are some works on the way about using AI to perform load management, and also you can use integration with the renewables. So a lot of things, even predictive maintenance is happening, right? Is going there to minimize our maintenance time and also to ensure our availability using AI. So it's a big it's a big technology that's going there. Of course, new battery technologies are coming up. In the last event in DCW in Singapore, some of you are there, able to visit. We have seen, I have personally seen some fuel cells are coming up. Of course, we have another battery technology which on top of lithium, we have the sodium ion that is really promising in the future. Again, all this battery technology also allow us to or enable us to perform things that we cannot do before, right? Like peak shavings, because now we can able to turn the UPS battery to online many times as we want, right? So because of this discharge cycles capability of new battery technologies. Grid support, it's coming. In Europe, it already started. In our region, in Asia Pacific, it's slowly, right? I believe in Taiwan, it's also being asked some of our customers in Australia, of course, because of the thing they will be retiring all their coal power plants, and they need to inject renewables in their grid, and this will call for better frequency regulations and grid support. And the UPS are a good candidate on this. And lastly, of course, everything drives efficiency in our UPS, because this is how we design. And one of the things that we can also improve in our UPS design that we are also looking is on the cooling technology. I was in the data center world again, and I see a lot of cooling solutions that they do for server applications. And the common questions that they ask us is, will cooling solutions can be also adapted in the UPS industry? I say, why not? Actually, it's been adapted before, and it's been also been used on other other type of electrical system. Our transformer, our MB transformer are oil cooled. They are immersed, right? So it's coming. It's just the right technology on certain applications. So it will be there, and of course that's bring us a bright future, right? For on how we develop new technologies and complement electrical designs or electrical architectures in the market. So with that, that ends my slide. I hope I stay within the time limit. So if you have questions, feel free to put it in the chat. I think we have like 6 minutes time of our webinar today. So if you have any questions, feel free to put them in the chat or the question box, right? And in addition to that as well, if you look on your screen, there are some available handouts that as reference for this webinar. There is some of the information about the product that I've showed with you, and some brochures as well, so you can download them and you can get through them. Okay, so let me just check if we have any questions on this one. Any questions?
Rachel, thanks for the presentation. It was wonderful. We have got two questions. One from Manoj Josh. It's in the question window, not on the chat. Can I read it for you? Or?
Okay, you can, because I don't see it. Sorry. Yes. Can you read?
Yes. Yes. Yeah. The Manoj question is, STS will maybe a single point of failure. So I don't know.
Yes, I think Manoj, you are right. This is a common misconception. I would say yes, it's because it's connected directly to the load. But if we look closely with an STS, right? Everything, if you open it up an STS, everything is doubled inside. You have dual power supply, dual logic control, dual path. You have your maintenance bypass. You have the dual control. Everything is dual. The only one that is not dual there will be the output cable, right? So I would say in terms of reliability, um, STS is one of the highest. In addition, it doesn't have any life cycle parts, right? The only thing that you have there is the fan, but it's not like our UPS, that a typical UPS where you need to replace capacitors, batteries, etc. Right? So STS is one of the most reliable system that you can see there in the market, of course. And those are the things I would suggest. Those are the things that you need to look at when validating an STS. The redundancy level they provide internally, how they are being built, right? How they are being processors, how they react in case of a fault, right? The resiliency, if there is a downstream transformer that will induce inrush, that will put into uh, an issue to the SDS. Those are the things I think I encourage everyone to validate, right? Because these are real things that can happen on the downstream and can put the SDS at risk. But I would say I'm not from Socomec, but I only know two brands that are good. But Socomec is one of them. They have all the things that I've seen to you. Dual power supply, dual controls, and all those redundancy internally as well as transformer management.
Thank you, Reason. Another question from Somachandar Kazam is, how can I watch your webinar offline again? Do we get then handout of your webinar? Somachandar, I think okay, I will answer that. So you will get a thank you mail with the webinar link so that you can play that again and understand more on that.
Awesome.
Okay, any more questions related to the topic what we discussed today, please? Okay, thank you, Ruhaibur. Thank you. Okay, I think Chandra Mohan said thank you, wonderful session. Ruhaibur also said that's awesome. Okay.
Looks good. Thank you, guys. It was also a pleasure for me to share with you. And I think we're gonna make a lot of these webinars to keep us connected. And of course, just feel free to reach it out also on what topic that you want to be discussed in the future webinars that we're gonna be sharing. Let us know. Keep in touch. I think Manish will be sending you some emails, and of course the brochures are there, and if you need any information or any questions, feel free to reach us. Manish, back to you.
Thank you, Reason. We need some session on POE. There is a request from Chandra Mohan. We need a session on POE.
Let me know that one. Yes. What is PUE? Is it a hype? Yeah, maybe that will be my title of my next webinar. PUE. Yes. Okay. Good suggestion. Yeah.
I think we are running out of time. So any questions or clarification, you can directly reach out to Raisin. I will share Raisin's contact on your mail directly.
Awesome.
Okay. Yep. Thank you all. Thank you for joining today's wonderful session, and thank you, Raisin, for the presentation. And it was really an insightful one for me as well as the audience.
Thank you.